Hello, and welcome to the first lesson of the third unit of grade 12 University Chemistry, Energy and Rates of a Reaction. In this first lesson, we're going to do a lot of definitions that get us started to think about the concepts of energy, energy transfer, and all the thermodynamic stuff that we'll be looking at in future lessons. There'll be a few spots where I'll say pause this video to watch some other videos, and I'll just let you know when that comes up. So, start off, we're going to define the system and the surroundings. So the system is wherever the chemical reaction takes place, and the surroundings is everything else. These two will be important to recognize when we're doing quantitative values to look at the energy transfer between the system and the surroundings. If we say that a system is open, that means both matter and energy can flow freely throughout the system. If it's closed, matter is locked within the system, but energy can still flow, and we're going to use the term an isolated system for when neither energy nor matter can flow into the surroundings. This can be visualized here in what we have a test tube, or what looks like a test tube that is open at the one end, would mean both energy and matter can flow within that system. Matter could leave either as a gas, or if you poured the contents out. A closed system would have that test tube stopped or have a lid on it so that matter cannot flow, but you could still have the transfer of energy. And then in an isolated system, there's some sort of material surrounding the test tube there so that no energy can flow. This would be the first time to stop and watch the TED Ed video, All the Energy in the Universe. Thermochemistry is the study of the energy changes that accompany a physical or chemical reaction. There's physical reactions that could be a change of state, chemical reactions, an example here is hydrogen burning, or you can have nuclear reactions, which we're going to look at in more detail in future lessons. All of these are accompanied with some sort of change in energy. Now, energy is changed by some sort of external force or some sort of chemical reaction, but we got to define what energy is. So here's an example of a carbon dioxide molecule where the three types of energy are shown. Vibrational, which is the motion involving the actual movement of the bonds. So you see bending, you see symmetric and asymmetric stretching. The second type is a rotational motion, which involves some sort of spinning of the molecule around one of the axes of the carbon dioxide molecule. And then translational motion is the actual whole movement of the molecule itself. All of these motions take place, but it depends on what state they may be. So if you're in gaseous state, then you have free translational, rotational, and vibrational motion occurring at all times. If you're in liquid, your translational and your rotational are restricted due to intermolecular forces. And if you were in a solid state, then there's no translational motion and you have some of that rotation restricted again. So all of these states depend on the temperature at which your substance is, which then directly relates to energy. So let's define heat and temperature now. Temperature is the average kinetic energy, so it's all of that motion that we just talked about, and it's often measured in degrees Celsius or Kelvin, whereas heat is the amount of energy transferred between substances, and this is measured in joules. Temperature is given the symbol capital T, where heat is a capital Q, which makes sense. This would be the next time to pause this video and watch Veritasium's video on the misconceptions about temperature. So, talked about energy transfer being one important concept that we're going to look at in this unit. The flow of energy is between the system and the surroundings, or a bunch of different objects that could be within a system, and we're going to look a lot into that actual transfer. If a reaction is deemed exothermic, it means you're releasing thermal energy. I always say when you're trying to remember the difference between exothermic and endothermic, exo, think exit. The heat exits the system, so it flows from the system into the surroundings, and you have less chemical potential energy in your products than you would in your reactants. The Q value will be negative. Whereas in endothermic, all of that is reversed. Endothermic, I say think enter. The heat will enter the system, meaning you have more stored chemical energy in your products than you do your reactants, and thus a positive Q value. The type of energy will also matter when you're doing the transfer, because you could transfer some of that kinetic energy into chemical potential energy. So let's define kinetic energy as moving electrons or vibrational, rotational, and translational movement of atoms or molecules. Whereas the chemical potential energy is the actual energy of the bond or the intra or intermolecular forces. Here is a diagram showing that energy is not lost. You have this reaction between hydrogen and oxygen creating water, and that red line shows that there's a total amount of energy is constant throughout the system. In your reactants with the two gases, there is more chemical energy than there is when you have the new bonds formed. The peak in the graph is seen here is the activation energy. When there is enough heat or light energy put into the system, whereas the chemical potential energy has reached a certain peak, then the reaction will take place and your products will be formed. And this is the change in some of this chemical potential energy into heat and light energy. So this would be an exothermic reaction, as energy is exiting the system as heat and light. There is no change because energy cannot be created or destroyed. The specific heat capacity is the amount of energy required to raise the temperature of 1 gram of a substance 1 degree Celsius, or degree Kelvin, depending on what unit you're using. The equation that we're going to use is Q equals mc delta T, where Q is the heat being transferred, M is the mass of the sample in grams, T is the change in temperature, and the specific heat capacity is C. I always say keep track of what units you're using. Sometimes they're given in joules per gram, joules per kilogram, kilojoules per kilocalorie. Sometimes it's degrees Celsius or degrees Kelvin. So you may have some unit conversions that you need to do if you're given like the mass in kilograms, but you're given the specific heat capacity in joules per gram degrees Celsius, or if you're given temperature in kelvins or any other different iteration. The heat capacity of a substance is dependent on the 3 ways that the molecule, atoms, or ions can store that thermal energy. So the higher number of atoms often have the stronger bonds, and then the higher heat capacity. So that's a little table there kind of showing that. Temperature is a measure of the average translational energy that it is striking the thermometer, as we talked about, or as you saw in that other video attached to this lesson. The heat of fusion and the heat of vaporization are when you're changing state, but no temperature change has occurred. So you can see that these two equations are very similar to our last one, the Q equals mc delta T, but here there is no delta T, there's no change in temperature. And the heat of fusion and heat of vaporization are both constants depending on the substance that you have. One is going from solid to liquid, and one is going from liquid to gas. So it's just dependent on the mass and the type of substance as to how much energy would be required to change the state. Let's look at the example of water, where we know the melting point of water is 0 and the boiling point is at 100. This is the temperature of water and the energy supplied to a system. If you started at the bottom of this graph here at negative 100 degrees Celsius and started to put heat into the system, your solid water would begin to heat up. You would probably have more vibrational energy occurring to the point where it gets to 0 degrees Celsius. Then you would have ice, so solid water at 0 degrees Celsius, changing into liquid water, but you'd have to keep putting in some amount of energy for that physical change to occur. You can have both liquid water and solid water at 0 degrees Celsius, depending on where within that physical change your molecules are. Putting more energy into the system would raise the temperature of the liquid up to the 100-degree point, where you can see it takes a lot of energy to change the state from water to steam. And then that would continue on, raising the temperature of the steam as you add more and more energy into the system. This leads to the last slide here, where we're talking about and introducing the concept of enthalpy. So it's not possible to measure all energies for a system. You can't say, well, there's this amount of light and heat and chemical potential energy and kinetic energy all within the system. So we look at the change. We look at how much energy is being absorbed or released into the surroundings, and we say that that is the change in the enthalpy. The first law and our first enthalpy equation would lead to the delta H, so the change in enthalpy being equal to negative Q. Q is negative in this case because no energy can be lost or destroyed, so this is the transfer of energy from our system, Q, into our surroundings in which we are measuring. Some examples of this could be you have a chemical reaction occurring in water and you're measuring the temperature of the water. The chemical reaction is the substance that you are, maybe to say you're dissolving it in the water, whereas the actual surroundings are the water. So you're measuring how the substance that you put into your solution changes the temperature of the surrounding. You're measuring how dissolving, so a physical change in your substance in water, changes the temperature of the surroundings.